Now I'm recording. Okay, so convergent, divergent. Okay. So C, okay, if both negative infinity to a f of x dx and the integral from a to infinity are convergent. Okay, are convergent. Okay, then we define the integral from negative infinity to infinity of f of x dx, negative infinity to a of f of x dx plus, okay, so we can just add the parts. Okay, as long as they're convergent. If they're divergent, all bets are off. Okay. Okay, so let's do an example with our newfound knowledge. Okay, number one. Okay, determine okay 1 to infinity of 1 over x. Oh, there's our friend again. Okay, is convergent or divergent? Okay, is this convergent? Is convergent or divergent? Or divergent. Okay. So 1 over x, and we have a special name for this too, which we'll talk about later. But this is the harmonic series. This is called a harmonic series. Okay, which we'll talk about later on when we talk about series. Okay, and we're going to find something about the harmonic series right now. Okay, you know, does this converge? Does this diverge? Right. This is the role of the harmonic series. Remember, we worked with this yesterday when we wanted to find the integral from 1 to 2 of 1 over x, right? Remember that? Okay. And we're doing the approximations, and we just said, oh, well, this is just equal to natural log of 2, which was, and we just wanted to find all those approximations. So we're working with the same sequence, or the same function here, 1 over x. Okay, but now we want to go, instead of just 1 to 2, we want to go forever. Okay, and we want to see, okay, what's going to happen here. Okay, so let's say that 1 to infinity of 1 over x dx, as t goes to infinity, of the integral 1 to t. So again, we plug the dummy variable t in so that we can make this a limit, okay, of 1 over x dx. Okay, so now let's integrate this. Well, the integral of 1 over x is just natural log with the limit, the limit as t goes to infinity, okay, of this thing. So this is going to be natural log of t. So this just ends up being the limit as t goes to infinity, okay, of natural log of t. Well, this is just the limit as t. What's the natural log go to? If you look at the graph of the natural log, it looks like this, right? And so as t goes to infinity, what happens to the function? So this thing goes to positive infinity. Okay, and so since the limit of the natural log function goes to infinity, which is the integral of 1 over x, then we can say this thing is equal to infinity. Therefore, the limit, okay, the limit does not exist, okay, and okay, therefore the limit does not exist, and the integral from 1 over infinity of 1 over x dx, okay, it is divergent. So why is it divergent? Let's explore this a little bit better here. Okay, when I look at 1 over x squared, okay, this is going down really fast. Okay, so 1 over x squared. Maybe we'll just bring up Desmos real quick. Take a bite of my lunch, late lunch. It was poor planning of mine to heat up my lunch at 2:20, but I was in office hours. I didn't want to wait until 5:30 to eat my lunch, because then I would have just ended up skipping lunch, which is probably not good. So I will be periodically eating in front of you, and that may be rude. Environment. is equal to the limit as t approaches a from the right, f of x dx. Okay, and then let's look at a graph of this one. Okay, a little diagram of this one. If we're going from b now, okay, let's included, but a is not included this time, and t is any value in between, and we're going to be going this direction. Okay, and we want to, as we approach that, we want to get the area under the curve. Okay, as t approaches a from the right this time. Okay, again, if the limit exists. If the limit exists, we say that this is convergent. Then we say the interval is convergent. Otherwise it's divergent. Okay, if it doesn't exist, convergent and divergent. Okay, C. If discontinuity at C is less than B, okay, and both the integral from a to c of f of x, the integral from c to b of f of x dx, okay, are convergent, okay, then b of f of x dx is equal to the integral from a to b sorry, not from a to x dx. So c is kind of our middle value there. And why would we have to do this? Because sometimes we're going to get a discontinuity. Okay, it has a discontinuity. We could have a jump discontinuity. We could have a spike in the graph. Okay, and we're going to have to say, well, let's do the integral on the right side, let's do the integral on the left side, and then let's put them together. Okay. Okay, so let's look at an example of this. Okay, number 3. Okay, from 2 to 5, okay, square root of x minus 2. Okay, and what's weird about this is because there's a discontinuity at 2. Okay, the value at 2 does not exist for this function. Okay, so I don't know what this looks like. Probably go down pretty slowly, to be honest with you, at 2. Okay, and so it's just not included. So we just need to take the limit of this. Okay. Gosh, I did not want to do that. Let me get my white pen out here. There we go. Okay, and I want the integral. It's an open circle. Okay, from 2 to 5. Okay, so we want to do the limit. Okay, as t approaches 2, what, from the right, right, from the right, 5, because we have you know, this problem that, you know, our domain is 2 to 5. 5 is included, but 2 is not included. Okay, and so just by the nature of this rational function. Okay. Okay, if I go anywhere below 2, it also, the graph doesn't exist. The graph doesn't exist at 2, but also doesn't exist for anything below 2, because then I would get a negative value in the and under the square root, and it just doesn't make sense. Okay, so it kind of stops there. Okay, so 1 over the square root. This is going to be x minus 2 to the negative 1/2, right? Okay, x minus 2 to the negative 1/2. Okay, and so this is going to become what? Well, it's just going to become 2x minus 2 to the 1/2. You can do a u to u substitution on this. The problem is that u is going to equal x minus 2, and du is just going to equal dx, so it really doesn't matter, right? And then you just plug in x minus 2 back in for u. Notice that the only thing that went away and came back was the constant. Does that make sense? Okay. So this is going to be evaluated from t to 5. Okay. Okay, so we want of this thing here. Okay. That thing there. Okay, let's plug in our 5 real quick. So this is going to be 2 times 5 minus 2 to the 1/2 power minus the 1/2 power. Okay, and I want to take the limit as t approaches 2 from the right. Okay, so this thing, okay, this thing is going to approach 2 radical 3 minus this thing is going to approach 0, right? If I plug in 2, doesn't that thing just go to 0? And we're not dividing by 0 anymore, so that's not an issue. So that thing just goes to 0. Okay. So what's the area under the curve? Well, the area under the curve, okay, is 2 radical 3. Okay, so it converges. It converges to 2 radical 3. Okay, let's do another example. Let's do example 4 here. Okay, I have log of x dx. Okay. Okay, so we want to try to figure out what this guy's going to be. Okay. Okay, so notice that for the natural log, right, we cannot ever approach 0. So 0 would have to be approached from the right. Does that make sense? 0 would have to be approached from the right, and we would have to take a limit of this of the value here. Okay, the limit of this integral. Okay, from 0 to 1. So this is 1 here, right? And so, but we can never reach 0 with our function. We can never get there. Okay, it's going to go there pretty fast, but we can never get to 0. So we have to set up a limit. So the limit as t approaches 0 from the right of the integral of t to 1 over dx. Okay. So now what I have to do is I have to figure out, well, what's the integral of natural log? What is the integral of natural log? Well, you could look it up in a table of integrals if you really wanted to. It's x natural log x minus x, or we could derive it using integration by parts. Okay, the funner way is to derive it ourselves, so we know how to do this. We don't have to just memorize a formula here. This is x times ln x minus 1, actually. Okay, that's the integral of natural log of x, is this thing here. Okay, but let's use integration by parts to integrate this. Okay, du is going to be equal to 1 over x. Okay, so what integration by parts allows me to do is turn the integral into a derivative, and I'm able to work with the derivative instead of the integral. It's kind of nice, because the derivative of natural log is an algebraic function. And algebraic functions are nicer to work with. Okay, so then what's dv? Well, what's v? Think of this as 1 dx, right? 1 dx. X. Well, the integral of 1, yeah, thank you, Veronica, is just x. Okay, it's just x. Well, something really nice happens here, right? When I do uv, v du. Okay, so this is going to be uv minus the integral of v du. My u's and my v's look way too similar. uv v du, v not dd. Okay, v du. Okay, become x natural log x minus the integral of dx. Oh, okay. Oh yeah, there's a dx here. Okay, they're gonna get mad at me one day. Be the attack of the dx's. Stop neglecting others. Okay, so what's x divided by x? Well, that's just 1. What's the integral of 1 dx? We just saw what that was. That was, there you go. So we're going to evaluate this from t to 1, right? When the limit as t goes to 0. Okay, so what are we going to get when we do this? Let's plug this in. This is going to be 1 times natural log of 1 minus 1 with t minus t. Okay, and we want to take the limit of this. Well, the natural log of 1, this is a 1, by the way. 1 times the natural log of 1, the natural log of 1 is 0. Okay, so 0 minus 1 is negative 1. Okay, minus, okay, t times the natural log of t plus t. Okay, but what does t go to if t is going to 0? If t is going to 0, then isn't t 0? So doesn't that go to 0? Yeah. So again, I need to figure out what is this thing here? What's this thing going to? Okay, so as the natural log of 0, that doesn't exist. Okay, right, so I'm going to rewrite this, okay, into a form that makes a little bit more sense for me. Okay, so so that I can use L'Hopital's on this guy here. Okay, because right now I have negative 0 times what is this? The natural log goes to negative infinity times negative infinity. So I have this indeterminate form here. Okay, can't be determined. When I plug in the limit as t goes to 0, I get this thing here, right? Okay, so what I'd like to do is rearrange this so that gets me something a little nicer. So I'm going to say that this is really, okay, the limit as t goes to 0, natural log of t all over 1 over t. Okay, so this is t goes, right? So then this becomes negative infinity over infinity, which is fine. Okay, negative infinity over infinity, which now we have a good form that we can do L'Hopital's rule on, right? Okay, is it negative infinity? No, it's positive infinity. I'm sorry, it's a negative and times a negative, which is a positive. Because this thing goes to 0, this thing is infinity, so it's good. Yes, good indeterminate form there. Okay, and so what are we going to do? We're going to do L'Hopital's on this, right? So let's do a little h action from the right of the top. Okay, this is going to be negative 1 over t. That's the derivative of the top. This guy on the bottom is going to be negative 1 over t squared. Okay, negatives cancel. And this is going to end up being flip the denominator upside down, and that just equals t. So what does this thing go to? Well, this thing goes to 0. So that equals 0. Okay, so the only term that survives, okay, is this negative 1 here. Negative 1, it converges to negative 1. So what was the area under that curve? Okay, what does it converge to? Remember, what does the curve look like? Well, it's just our natural log curve, right? Again, negative 1. Okay, that's kind of cool. Okay, that's another negative 1 area. Okay, let's look at the comparison theorem real quick. Okay, so the comparison theorem, suppose, okay, our continuous functions are functions greater than or equal to g of x for x greater than or equal to a. Okay. Okay. A. Okay, so we're saying f of x is bigger than g of x, right? So this is a theme that we're going to revisit. What we're doing here, we're going to revisit this in chapter 11. This is kind of an intro to chapter 11. Okay, so A. Okay, if the integral dx is convergent, so then the smaller one is also convergent. Sandwiched between something that's convergent. If you're sandwiched between the x-axis and something that's convergent, you're going to have to converge too, if you're always smaller. Okay, I'll draw a graph to help illuminate that. Okay, then g of x dx convergent. Okay, and again, it looks like this. Say that we have a function f of x, okay, is some other function, okay, that's always less than f of x. Then wouldn't that be forced to converge as well? Wouldn't g of x that's always less than f of x, that would be forced to converge as well, right? Does that make sense? Because it's being sandwiched between the x-axis and, okay, it's kind of like the squeeze theorem. We're squeezing it between these two. Okay, so B, okay, if the integral dx is now divergent. So the smaller one diverges. Okay, then we can say a to infinity of f of x is also divergent. Well, again, the smaller one diverges, right? So the smaller one diverges, which means that if this is g of x and this thing diverges, and it's always smaller than f of x, then f of x must always cross. You don't ever want to cross the strings. Okay, learn that from Ghostbusters. Okay, so okay, it always has to be bigger than something that's divergent. It's going to be divergent. So if you're smaller than something that's convergent, you're going to converge, and if you're bigger than something that's divergent, you're going to diverge. Okay, so that's the idea here. Okay, so let's use this to do an example. Okay, show that the x squared dx is okay, and so I'm going to say that e to the negative x squared is equal to 1 over e to the x squared, right? Okay. And I'm going to say that this is, because x squared is going to give me a bigger number, right? And that's going to produce e to the x squared. This is going to be bigger, right? So the e to the x squared is going to be bigger than e to the x. We take the reciprocal of that, then this whole thing ends up being smaller, right? Dividing one divided by a big number is a small number, and 1 divided by a small number is a big number. So the inequality holds there. Okay, for all x. Okay, so what we can do here is we can say infinity of e to the negative x. Okay. Okay, so what's that going to look like? Well, it looks like this. E to the negative x looks like this. Oops, not like that. Looks like this, right? Okay, exponential decay. Okay, and it's going to converge. Well, we'll see. We'll see if it converges. Okay. So, since this guy, okay, since 1 over e to the x converges, then 1 over e to the x squared would also have to converge. It's going to converge faster. Okay, so compare this guy to my original, and we're going to say, oh, well, let's see if this guy converges, what he converges to. Okay, so we're going to say that the integral of this thing is going to be the limit as t goes to infinity of e to the negative x, which is equal to the limit as t goes to infinity of what? What do we got here? We've got the integral of this thing is going to be negative e to the negative x, right? Okay, so this is negative e to the negative x. Okay, the derivative and the integral are the same thing here. Okay, pretty sure that works like that. Yep. So, yep. Okay, we could do a u sub on that, but we just end up with a negative sign. Okay, and then evaluated from 1 to t as t goes to infinity of negative e to the negative t minus negative e to the equal to the limit. Come on. The limit as t goes to infinity of plus 1 over e to the first power, which is just e. Okay, so 1 over e. Okay, so then what happens as I plug infinity in here for t? This goes to infinity, so this whole thing goes to 0, and so I'm just left with 1 over e as what it converges to. So this thing here converges to function f of x was equal to 1 over e to the x. Then the e is just 1 over e. Kind of interesting. Okay, that's the area. Converges. Well, we also know that 1 over e to the x squared is going to converge even faster. Okay, let me use a different color here. Okay, this thing's going to converge whoosh like this, boom. And so if that thing converges even faster, then it's sandwiched between the two, and so we can say by We don't know what it converges to, but we just want to know whether or not it converges. That's all we care about. By the comparison theorem of e, what do we got here? E to the negative x squared converges. Okay, because for all x, this one's less than the other one. Okay, so it does converge. Okay. Okay, so that's it for new material. Okay. So I'm gonna at this point, if you have any review questions, let me know. Okay. Okay, well, you think about it for a second. I'm going to go freshen my cup. Okay, I'll be right back. Okay, what do we get here? Got a live one. Hi, can you post a recording of this lecture tonight? Yes, Robbie told me his internet connection is bad today, so he missed parts of the lecture. Sure, absolutely. I can. Okay, number 14 on the review, Veronica says. Okay, let's bring up the review here. Okay. Okay, number 14. To the nearest, okay, estimate the area of the shaded region by using the trapezoidal rule with n equals 2, round the answer to the nearest 10th. Okay, so we're going to use the trapezoidal rule here, right, with n equals 2. Okay, so we're only gonna, I wish I could write on this, maybe, okay, so we're gonna take f of 0, okay, you can use it, oh, okay, cool, okay, cool, can you annotate? Yeah, I can. Okay, perfect. Okay, so let's get rid of this. Okay, so I only want 2 divisions here, and it goes to 6, right? So I'm gonna look at this thing here. I'm gonna do my trapezoidal rule, right? And so I'm gonna go from, and try to draw a straight line. I'm gonna try to, and then I'm gonna create another trapezoid. So I've got 2 trapezoids. I actually have just really one big trapezoid because they're the same slope, but we may not know that initially. Okay, so what we want to do here is we want to do delta x over 2 times, okay, f of 0, okay, plus f of 6, right? That's how I'm going to get my trapezoids here. Okay, so what is f of 0? It looks like f of 0 is 1, 2, 3. It's looking like 3. So what's delta x? Well, delta x is 3, right? So this is 3 over 2 times, okay, f sub 0 is 3. What's 2 to 6? That's 1, right? Okay. So this is going to be 3 halves times, this is 3 plus 4 is 7 plus 1 is 8. So the whole thing comes out to be 12. Okay. Okay, others? Okay, number 5. Okay, let's see what number 5 is here. Okay, find the area bounded by these curves. Okay. When x equals 0 and x equals pi over 2. Okay, so this one's going to take. Okay, so we have y equals. Okay, and this is number 5. Y equals 3 cosine squared x. We want to know what's this going to be bounded by, right? Okay, so I could set these equal to each other and find out what they're going to be bounded by. What did I think it tells me here? Oh, we just want to know 0 to pi over 2. Okay, the area bounded by the curves between 0 and pi over 2. Okay, that's fine. So, okay. So we want to know which one's going to be on the top and which one's going to be on the bottom. Okay, which one's going to be on the top and which one's going to be on the bottom. So of x is between -1 and +1, right? Okay, cosine of x is between -1 and +1. Okay, and the cosine of x squared is also between -1 and +1. Okay, but notice that when I do cosine squared of x, on the endpoints, it's the same, but everywhere else, what? Everywhere else it's lower. Why? Think of the cosine of x being equal to 1/2, right? If I square that, isn't that less? Every time I square a fraction, it's going to be a smaller number. Okay, smaller absolute value. So the one that's on the bottom is going to be the squared function, and the one that's going to be on the top is the top function. So so we want to find the area in between these two. Okay, so I'm going to take 0 to pi over minus 3 cosine squared x dx. Okay, to find the area in between. Cosine function looks like this. Okay, but I don't know what this cosine squared function looks like. Maybe it looks like this, the area in between the two. Okay, and this is going to be not 0 to 1, this is going to be 0 to 3, just because we got that 3 in front. Okay, and then this is 0 to pi over 2. Okay, so this is the setup. So what I'm going to do is I'm going to break this up into 2 separate integrals. So this is 3 times the integral of 0 to pi, pi over 2 of cosine squared x dx, okay, times sine x from 0 to pi over 2. Okay, the sine of pi over 2 is 1, sine of pi over 2 minus the sine of 0, 1, so 3 times 1 is 3. So I've got 3 in the front here. Okay. Okay, and then for this guy, this one's a little bit more involved. We've got minus 3 times 0 to pi over 2. Whenever I have a cosine squared and it's just by itself, I've got to use a half angle identity here. And I always remember, okay, cosines are being added. Okay, so the cosine is the addition, the sine is the subtraction. So, because s goes with s, right? So sine, subtract. Okay, so this is going to be 1/2 plus dx. Okay, when I use my half angle identity there. Okay, so this thing is just going to be 1/2 x when I integrate that. This guy is a u substitution. Du over 2 is equal to dx. Okay, because I would have divided by 2. Okay, and I get my d over 2 is equal to dx. Okay, blah, blah, blah. Okay, and then we're going to get, this is a minus 3 on the outside, plus the integral of, let me drop this down, it's going to be 1/2 times the integral of cosine u, right? Cosine u. I'm going to go back to x's in a minute, okay, just because it's going to make me happier by plugging in. I mean, I don't have to. I could change my limits of integration here. I'd have to keep this 0 to pi over 2, but I could, if I wanted to change my limits of integration, I would have to multiply, and so this would be 0 to pi. Just keep that in mind. If we use du's, we have to change our limits of integration. Okay, so we know 0 to pi of cosine u, so this is sine u. It says 1/2 sine u from 0 to pi. Well, that's kind of interesting because what's the sine of pi? That's 0. What's the sine of 0? Well, that's 0. So this whole thing goes to 0. Okay, it's just 0 minus 0. Okay, and so then we're left with 3 minus what? We're left with 3 minus 1/2 times pi over 2. Okay, why? Because if I plug in this 0, it just goes to 0. That goes to 0 as well. Okay, so this is going to be 3 minus 3 pi over 4. And that's it. That's my answer. Okay, that's the area between those two curves. Okay. Okay, others? Okay, another one from Victor, 8. Okay, let's go over number 8. Will you be on Zoom again tomorrow during the exam? Yes, absolutely. Okay, I'll be here. Okay, number 8. Oh yeah, number 8 is fun. Okay, partial fraction decomposition on this one. Okay. Okay, so it says find the volume of the resting solid if the region under the curve, okay, is this, okay, solids of revolution. So this is pi r squared, right? So pi r squared from 0 to 1, okay, rotated about the x-axis. Okay, so from 0 to 1, that's r, right? And sorry, that's 0 to 1 is where we're going, and then our radius is just our function squared. Okay, so I don't know what this function is, some sort of, some sort of rational function, x squared plus 3x plus 2, 1 over x squared plus 3x plus 2. Okay, so again, that's some sort of rational function. I don't know what it is, but we're going to rotate that around the x-axis. Let me show you how this is done. Some rational function here, right? And we're going to rotate this about the x-axis. Okay, and we're going to rotate it from 0 to 1, right? And so how do I get my radius? Well, my radius is just my function, f of x. Okay, and so we want to take these slices, right? And we're going to sum them all up. So doing these slices, okay, is r. So how do I find the integral, okay, of 0 to 1 of pi times f of x, and I get 0 to 1 of 1 over, okay, quantity squared dx. Okay, so now let's factor the bottom. Okay, the bottom is going to get factored into x plus 1 times x plus 2. And that's squared. So the top is squared and the bottom is squared. So these are dx. Okay. So now what I can do is do my partial fraction decomposition on this. So we have 1 over x plus 1 squared, a over x plus 1 plus b over x plus 1 squared. We have to take into account that either of them could be factors, plus 2 squared. Okay, so now I'm going to multiply through and try to get some values here. Okay, and turn this into a partial fraction. Okay, and then we can just integrate, hopefully pretty easily. Okay, so the hardest part on this one is getting the partial fractions. So I'm going to multiply through by the denominator. Okay, 2 squared. Okay, multiply this guy by everything. It's kind of sloppy. X plus 1 squared, x plus 2 squared. Okay, and so plus 1 times x plus 0 problem. So you don't need a bx plus c over correct when you have an x squared plus some value. Okay, so yeah, you need to know whether or not these are linear factors or quadratic factors. Okay, if it's a quadratic factor, then you have to have a linear numerator. If it's a linear factor, then it's a constant numerator. It always goes down by 1 power. Okay. Okay, so b times x plus 2 squared times x plus 2 times x plus 1 squared. Okay. Okay, so now let's go for our obvious values that we want to get rid of. So I'm going to let question. Okay, raising doesn't make it quadratic. No, it's a linear factor squared. The thing is that it's factorable. So here's the deal. Okay, the deal is that if you really want to do bx plus c, you can do that is equal to 0. Does that make sense? Okay, sounds good. You got some b is equal to 0. Yeah, there you go. There you go. Okay, that makes sense. Okay, so again, it's just, yeah, you're always going to get b equal to 0 if you create a bx plus c when you should only have a c. Okay, so let x equal -1 here, and what goes away? Well, everything goes away except for b, right? And that's just going to be b is equal to 1. Okay, if I solve that. Okay, so b is equal to 1. Okay, now let's let x equal -2. Oops. Let x equal negative, what the heck happened to my pen? -2. Come on. Come on. Don't do this to me. Be nice. Be nice to me. It froze. It frozen. Everything froze. Lovely.